Okay, so so we're going to do more of the. I'm going to talk a little bit more about the vibrating string problem. So, but I want to show. So these are standing waves. Okay, so the objective here is to understand how to solve PDEs by separation of variables. And also we have, in particular, the wave equation for standing. So the wave equation. For standing waves. Okay, so this is section 13.4. So we've jumped a little bit. Okay, so this section here, I don't think I've been good at pointing out the sections, but I want to point them out. So this is section 13.1. Okay, and the difficult part of the problems in this section here, when you guys do them, you'll have a differential equation. You can plug in the separation of variables. You get two differential equations, right? And the hardest part of this will be solving the actual ordinary differential equations. So that might require some refreshers, but it's at the but I think we did some warm-ups for these, and I think you guys should be okay. But I want you guys to try these, the things in section 13.1, and then tell me how you're doing. Okay? I kind of want to talk about a little bit about where we are in the book. And then I'm going to recap what we did. And then I'm going to do some stuff on the computer. I'm going to take that solution that we did yesterday, and I'm going to put it into the computer so we can see the vibrating string. Okay? So so let me just say that so we have done so section 12.3. So this is Fourier series, and so we need to do. This is Fourier, right? It's Fourier series, right? So there's a Fourier transform, which we might talk about in a bit, but we need to talk about section 12.4, which is Fourier series, so complex Fourier series. So that's with complex variables. So these are really real Fourier series. So this is the thing that you guys we just took a quiz on. So there is a section that I put on our objectives, which is 12.5, which is these Sturm-Liouville problems. So so for now, this thing here. So this is the V. So we'll need these eventually, right? So these are so these will be types of ODEs, certain ODEs. ODEs we need to deal with. Just to solve the differential equations we get after separation of variables. So this is another thing we can punt on. So we can so it'll get more complicated, like we had those boundary value ODEs, right? They can get pretty hard, right? But we can deal with this when they come up for the first time in an example, okay? So after this, so you guys should be in good shape to read. So we've talked a little bit about the different equations at the very beginning of the class. So what I want you guys to do is I want you to read 13.2, and I guess, yeah, 13.1 and 13.2, right? Okay, and so these are the basic equations. We've talked a little bit about this at the very beginning, but I didn't have you guys do problems, okay? I want you guys to do so it's 13.1. So I want you guys to do the problems for these two things, okay? Also, you can do the problems for 13.4 now. So 13.4 is this how we solve the wave equation, okay? So you guys should try those. Also, so then I'm going to talk a little bit about this, and then we're going to be pretty much done with chapter 12, except for when we need to go back here, okay? And then we'll come back there as we need it. So once it comes up in a PDE. Okay. So, so now I'm just going to do a little recap of what happened last class, because last class was kind of a slog through the computation, the solution of the vibrating string problem, okay? So, okay, so we had the vibrating string problem. Let me just say what it is. It's a boundary value, initial value, ordinary differential equation, okay, that describes the motion of a vibrating string. Okay, so we had this equation, V, right? So here, and x is in some interval, let's say 0 to L, okay? And then we had our boundary conditions. The boundary conditions were that the endpoints of the string were fixed, okay? So we'll modify these in a bit, but for right now we've been talking about fixed, so 0 t for all time. This thing is going to be equal to 0. So the endpoints of the string are fixed. And then we are supposing that we have some initial displacement, x0. So this was u naught of x. So this was this initial placement. Okay, and then we had ut of x0. So this is like the velocity of the string. So really this is the y-coordinate from 0, right? So so we have kind of like a line, and then we're having a function. The function changes over time, okay? And then we're saying the velocity is 0. So it's like we take the string and then we just let it go, okay? So we proved. So we showed. I guess we didn't really prove. Well, we didn't talk about convergence or anything, but we showed that. We get a solution. This problem, and so what did we have? So we had that u of xt was the sum from n is equal to 1 up to infinity of these coefficients a. So we had these things, and we had a cosine of. So now we have pi n v. This is a velocity, not a frequency. T sine, okay, times sine pi n L times x. Okay, so this is this was our solution that we got. And so we obtained the coefficients of this thing, these ANs here. So these coefficients come from the initial data. So we write u0 of x is equal to the sum. So we do this eigenfunction expansion of this function here. So we're using the magic that these guys here, so that these things form a basis, okay? And so then we have formulas for what the ANs can be, i.e. So an is the inner product of u0 of x with sine pi n over Lx and over the norm of pi n over Lx here. This norm squared. All right, so that's the norm over the interval 0 to L. Okay, and this thing denotes that you take these two things, you put them together, and then you integrate over that. Okay, so we did this eigenfunction expansion, so we can solve for these. These are going to be numbers, right, once we give a function. And then this gives us our solution. And this thing was so remember we did separation of variables. We got these xn's, right, from the boundary value problem. And then after we figured out what the eigenvalues were, right, and what the eigenfunctions were, we could figure out we got initial conditions for the t variable, for the other part. Okay? Okay. So all right. So yeah, like I said, that these solutions here, these techniques should allow you to start solving these problems in 13.4. Okay, so now we've written down this solution. Okay, and we picked a particular u0 of x last time. And what we did was I kind of punted on what these coefficients were because there were some nasty integrals. Okay, and it doesn't matter what they are. You just have to compute what these integrals are and then plug them into the series, and this will give you what you want. Okay. All right. So I think that we should now take this thing and put it into the computer and see if it does what we want it to do. Okay. And so we want it to act like a vibrating string. Okay, so let me copy down that equation over there on the other side, and I'll bring down the screen, and then we'll pull up. Okay, so let's pull up the solution here. So we have, so I'm going to write this. By t sine n pi over L times x. Okay, where u0 of x okay, and then an, right, this is this thing here over the norm of this thing squared. So that's just the integral with itself squared. So this thing squared. Okay? So I guess this is the norm. We call this the L2 0 of L space. Okay, so that's the interval 0 of L, and those are like the space of functions which are square integrable. Okay, so things where you can take inner products. Okay, so we have our formulas here. All right, so now I'm going to put this down. Cancel. Okay. All right, maybe I can put this over around too. All right. Okay, so let me close this. Close that. Okay, so so I started a new worksheet for us to talk about what we're going to do. Okay, so what I want to do is I want to plot this series here, right? And I want to do some sort of animation for it. So there's a code. There's some stuff in this for Sage. So you can Google, Sage animations, right? So animated plots here. So CoCalc, this thing runs off Sage. It's an open source alternative to Mathematica, Maple, and Magma, right? Okay, and so here, let's just try to copy what they do here. Okay, so they're going to take a bunch of sine functions, and they're going to animate them. So let's take this, let's put it in here, right? Okay, so they made a bunch of plots. So here they did plot of this thing, this function, on this interval. And then they did some coloring thing. I guess this color doesn't really matter. Okay, well, let's keep the y min, y max. And then for c in, let's say c in range. Okay, and so now for this thing, they're saying 0, 1, and they're taking a step size of this, 0.2. Okay, so that's what we have. We have this, and then let me. Okay, you can press Shift and Enter to do these quickly. Okay, so then we make the animation with this command A, and then you animate. So this is just kind of an array of plot objects. Okay, so you have that, and then I think you can do A dot, or so you can just type A, or you can do A dot show, right? So so you can always like do dot, and then if you press tab in Maple, or in Sage, it'll bring up a list of commands for you that you can call, right? So so it says tab complete. I guess not tab, it's just tab, right? So you can do show, right? So we'll do show, and it'll go like this. And also, if you want to know what the command does, you can do show. Oh, okay, so it'll do this. Let's see what it does. Okay, so this will make like a little animation like this, okay? So this is how you make these animations. So also, if you want to see what a command does, you can do like this little question mark thing at the bottom. And what it'll do is it'll bring up some documentation about what these things take. And then I think it'll have some examples, right? Like, yeah, here. Oh, well, this is a kind of a complicated example, but yeah. So they'll have stuff like this. And so Sage actually, when Sage compiles, it actually checks these examples every time. So this is a way it tests, it makes sure that the old code is still working when you make an update. Okay, so we have this thing, and what we want to do is we want to do this function for a bunch of different t's. Okay, so I did this before class to make sure everything worked. Okay, so let's look at what I'm going to have here. Okay, so let's take a function. All right, so let's pick a function. Okay, so let's go here. I'm going to show you what I'm going to do. So I'm going to bring this over to my other thing. Okay, so I'm just going to kind of copy what I did before. But here, this thing, so this sets the number of terms that we're going to have. Okay, so I'm going to make the truncation up to m, and then I'm going to compute. So then I'm going to pick a function. Does anyone want to have a function they want to try? So this is one I picked. Let me show you why. Let me show you why this picked. Let's see, plot u0, u0. So this is our initial data, x0, 1. I picked this one because it's like, oh, I can tell you why I didn't do our absolute value one, because the integrals are somehow kind of funky in Sage. If we were going to try and run this command here, so let me show you what happens. So like if I try and run this command for 1/2 minus, and then the function for absolute value in Sage is abs, and you do x minus 1/2. So this thing here, okay, let me run this. This thing is it's gonna output something, but these are okay, let me also point out what these coefficients are. So what we've done is we've taken our basis, so this sine n pi, and then we've integrated on the top here, that's this integral, and we divided by the integral on the bottom, right? That's this integral here. So we're integrating sine with itself, and that's what the norm squared is, okay? All right, so all right, so this is what this function looks like, but okay, let me show you. I put in the other function, I believe. Okay, so this is our like pyramid function. We could put this one in. This is this function where L is equal to 1 and V is equal to 1. All right, so we're looking at this particular example, but with our triangle function that we were playing with in the previous class. I just wanted to show you what happens with the integrals here, A. So there's some weird imaginary numbers coming up with how this is handled. So I think there's a bug here. So I'm not exactly sure what it's trying to do. Anyway, let's not do that. I guess it's maybe assuming that x is complex or something. No, I don't know. It's not assuming x is complex. We did this I don't know what it's trying to do. Anyway, I couldn't get that to work before class. So what I'm going to do is I'm going to pick another function. So let's do x for now. Okay? So we have this, and then let me get rid of this box here. So x is just this one. All right? Okay. So now we have SM. We haven't computed. I want to compute the truncation of this series now. Okay, the truncation of the eigenfunction expansion. Isn't what? It doesn't fit the boundary conditions, but what it'll do, it doesn't really matter because the formulas will work anyway, right? And what it'll do is it'll like force it to come down. It'll just have really large error, right? So you can really just put any function you want in there, right? And it'll just pretend like it goes up and then comes down really fast. Okay, so it'll do something, right? That's a good point, though. It does not satisfy the boundary conditions, right? So that one is not connected at the bottom. But we can plug it in, and it'll give us something, okay? Okay, so let's do that. All right, so so now what I'm doing is I'm taking, so I have those coefficients, and then I didn't show you the SM. Okay, so now this is the, I need to specify an M. I already specified an M. M is 10 up here. Okay, you guys see that? I have 10 terms. So I'm going to do this sum. Okay, indexing starts at 0, so I have to do this weird thing where I go to n minus 1 here, and I have to make sure I add an extra term here. Okay, so there's some indexing issues, but okay. So I have this thing, and let's see what SM looks like. It should be 10 terms, right? Okay, so yeah, it'll have the constant term, or I think this is okay. This is, it's 9 terms, whatever. Okay, so all right, we have this thing now. Oh yeah, because it stops before there. Stops before, so it goes, yeah. Okay, so we have this function now, and let's plot it so you guys can see it's an approximation of this function. So plot SM, x in 0 to 1 like this. Okay, so this is like trying to be a line, and see how it just like falls off there, right? So that's you know, because it didn't match the boundary conditions, so this thing's going to force it to. And then the error is going to get nasty here. Okay, it's going to, okay. So we have that. Now we want to use the same coefficients, these ANs, to produce that function there. Okay, we want to do it for our solution of the vibrating string problem. Okay, so we have these two things. Okay, and so this is what this command does. So other than x, Z. Okay, other than x, for every other letter other than x character, you have to declare that it's going to be treated as a symbolic variable in Sage, and that's what this command does. All right, and all right, so let's go. And then this thing, you can see, it's going to take those coefficients and then multiply them times the cosine part and the sine part here. All right, so let's do that. Okay, so let's make our function here. So we have this u now. This is our u. And to make substitutions into u, you have to use a certain syntax. But I'll show you how to do that. Okay, so it's working hard at doing this. Okay, well, that's working. Let me see. Okay, so it stopped. Okay, so now we have 10 terms of this series. It's stored in that u. Okay? So, all right, so now what I'm going to do is I'm going to make the parts that I'm going to use for the animation. And so I guess what I'm going to do is I'm going to, so here, I set the number of times. I'm going to go about 6 times 5. So I'm going to go out to 30. T is going to be 30 at the end of this. So I'm going to go up to time 30, right? And then what I'm going to do is I'm going to take little steps. Well, I guess not 30. It's going to be 30 divided by 5 is 6, right? So, so I'm going to take these little steps. So I'm going to set in each one of these. This is a function of x and t. And what I do is I set t equal to the, a certain time, and then I'm going to do a plot. So I'm going to make a bunch of different plots here. Okay. And then I'm going to animate those things. So let's say B is equal to animate, right? Is that how we did at the beginning here? Animate frames. Animate frames. Like so. I guess it's still plotting. Go. Well, I have another one here. So I did this beforehand. So this is with a different function, but so b.animate frames. All right, let's see. Okay, there we go. Okay, so b.show. Okay. And hopefully everything works out. All right, while this is going. Any questions while this is going?
Will it still force it to go back down to 0 at your boundaries?
It'll force it to go back down to 0, yeah. And that's forced by the sign there. You can see that, like, if you plug, so let's see. So let's like plug it in. So what do we need to plug into? So we need to plug in, like if we plug in x is equal to 0 here, right? So if x is equal to 0 here, this thing is going to be 0, right? So that forces it to be 0. And if we plug in L here, right, then it's going to be a multiple of pi. But sine is 0 in multiples of pi because it's the y coordinate, right? So it's like at 0 at pi. So it's just like the y coordinate on the unit circle. And if you go at 0 and then you go at pi, it'll force it to be 0. Okay, so why is this taking forever? I don't know. Let me show you another one while we're waiting, I guess.
Is there any exception to that if it diverges at that point?
So what it'll do is, what do you mean if it like if we were going to plug in like 1 over x, like something 1 over x minus 1 or something where it goes like off to infinity?
Yeah, something like
so then the integrals, so then you have to be worried about if the integrals converge. But then you could pick a convergent integral, and I actually don't know what happens. So like, yeah, you could probably, I don't know. I don't know what happens, like off the top of my head. But yeah, that's kind of a fun thing to do, right? Is to try and see what happens when you plug in something weird. Oh, there we go. So this is ours, this is the other one. What the hell? Okay, so let's just do this one. Let me show you. I picked for this one, I picked another function. I picked this function here as instead of that line. And what this one does is it does this. Go. So it goes up and down like this. Okay, so yeah, and you can see that it's vibrating like a string here. All right, let's see if this one goes. I don't know what's going on with this show, so we can do stop. Okay, well, I'll attach this one, but at least you guys saw one of them here. And so, okay, I'll send you guys some other notes on why this is like not physically accurate. So there's a lot of dampening that energy is lost, and so don't actually try and apply this, right? It's not accurate. Okay. All right, so that's that.